Okay, so this is a recording of a lesson on the skeleton and muscles. Again, like with the last video, this is a revision chapter, like we said we would do. So we're just going to get straight into it because this one's probably going to be a little longer than the last one. The last one was, I think, 25 minutes. This will probably be half an hour to 35 minutes based on a number of slides. So let's get started, all right? So we're going to have a look at the skeleton and the muscles. You never really study one by itself because they kind of work together. You know, without skeletons, you wouldn't have muscles. Without muscles, you wouldn't have skeletons, all right? So quick introduction. The skeleton works with the muscles in the body. Together, they're referred to as the musculoskeletal system. A little bit of a mouthful, but that's what it's called. The system is controlled by the nervous system. So your brain, once again, is the big supercomputer in your body regulating everything that's going on. All right. Skeletal muscle is any muscle associated with the skeleton. We'll have a look at that in a little bit more detail later on. And other muscles include cardiac muscle and smooth muscle, which we see in the intestines and the heart. And we'll talk about them. I think literally the very last slide we refer to them, or one of the last slides anyway. So what are the main functions of the skeleton? Some of these you might have guessed. So first of all, support. It keeps the body upright. So it keeps us standing, basically allows us to fight the pull of gravity and be able to, well, stand. Protection. So if you look at the skull protects our brain. The spine protects our spinal cord, two crucial organs. And then our ribs protect vital organs such as the heart and the lungs. Movement. Muscles allow bones to operate as levers, all right? So they pull against the bone, all right? And they allow us to move. And shape. They give us our shape. That's, that's why humans look the way they do. That's our shape. And finally, one that you may not have been aware of is that some of your bones will make blood components, particularly your long bones like your humerus, all right, and your femur down in your leg, all right. Those guys will make blood cells such as red blood cells, white blood cells, and your platelets. Okay. So I lifted this diagram from the book, all right, and it's a good one because it kind of just shows the two main types. So you've got your axial skeleton. This guy is on an axis, all right, so there he is, all right. That's your axial skeleton, all right. And then the appendicular is basically the bits on the outside, all right. So there's one appendage, there's another appendage, all right, hence why it's the appendicular skeleton, all right. I don't know why I'm drawing this whole thing out because I'm sure you've gotten it by this stage, but there you go, all right. And so they're the two main things that your skeleton is split up into. So the axial skeleton consists of the skull, your spine, and your rib cage. All right. While the appendicular skeleton, as you can see, has a lot going on for it. Okay. And we'll talk about those in a little bit more detail shortly. So we'll start with the axial skeleton. So there's a skull. All right. The spine and the ribs. So as we said already, or no, sorry, I assumed that the next thing was going to be that it protected the brain, but it's also known as the cranium. It consists of 22 bones. Most are fused together. So there's a diagram we'll see later on where we look at fused joints, and you'll see that the skull actually has a lot of fused joints. You can kind of see one there, all right, but it's not really great. Here is an example of a non-fused joint, your mandible, also known as your jawbone. Obviously, you don't want that to be fused because then you wouldn't be able to speak. All right, the mandible jawbone is not fused, and oh, hang on, if I remember correctly. Ah, I think it does a fancy thing where it spins around. We missed it. Doesn't matter. The axial skeleton, the skull and the spine and the ribs. So here is the spine, all right, made up of 33 bones called the vertebrae. Now the spine is a little tricky because it's made up of a few different parts. It's kind of got this area here. This is called your cervical region. This region here is called your thoracic region. And this region down here is your lumbar region. All right. So this area here, as you can notice, the vertebrae are quite big. These guys take a lot of the loads. When you carry something, a lot of the force is applied to this area here. Hence why you have these big, thick bones. All right. The top 24 can move slightly due to being held by ligaments. So basically, the ones you can see here, Ligaments allow them to move slightly, but these guys are all fused together. All right. Discs of cartilage lie between each one. Kind of hard to see in this, but basically where those lines are there, there's a disc of cartilage. This allows for shock absorption and it allows for a reduction in friction as well. All right. Not too surprisingly, you don't want your spine to overextend too much because that can damage your spinal cord, which can lead to paralysis. And as we said, the last 9 are fused together. They don't need discs, and they form what's called the sacrum and the coccyx. Now, I think, yeah, it's going to spin around here. Your sacrum is this guy here, and your coccyx is this down here. A vestigial remnant of when we used to have tails. All right. Who's buzzing me? Okay, so the last one then, guys, is the ribs. Oh, sorry, that's actually the one coming up after this, but this is a typical vertebrae. So the neural spine is where muscular attaches these kind of parts here, these spiky bits, all right? This is the neural canal. This is where the spinal cord will run through, all right? The centrum, that's this big thick piece here, that gives strength. And the facet where the vertebrae rotates against the next vertebrae. So it's kind of these little bits here that kind of slot in together. All right, kind of be more apparent if this starts to turn around. All right, so there you have it there. So these guys kind of, and there's a little gap there that slot into the next one, kind of like a chain link. It's kind of handy. All right. Oh, and the transverse process is just more. So I think if should have put labels in, but basically this is the neural spine where muscular attachment here, and then further attachment happens at these guys here. Okay, so the axial skeleton, last one, is the ribs. Okay, there's your sternum. All right, one big block in the front with these ribs floating behind. Now I'm pretty confident this isn't a human rib cage because it looks a little bit, well, it just doesn't look right to me. But anyway, it's a rib. It's got 12 pairs of ribs that make up your rib cage. The top 7 are attached to the breastbone. So see these guys, 1, 2, 3, 4, 5, 6, 7. These guys are attached to the sternum, and therefore they're referred to as true ribs. All right. You can also have false ribs where they are attached to each other. So look, they're not actually attached to the bone at all. So if you have a look, there's 1, 2, and that third one there, they're all kind of stuck together. See that? They're attached to each other in that section there. And then you have floating ribs. These 2 guys down the bottom here. They're not attached to anything except this area here. And just turning around to show that there. So you can kind of see the 3 guys attached together. All right. And there's 3 floating ribs in this diagram, which makes me wonder if that's actually a human rib cage at all. But anyway, moving on. The appendicular skeleton then is split up into kind of 3 main parts. You've got the pectoral girdle. So, you know, your pec muscles here, okay? The girdle just refers to this area around here, okay? So the pectoral girdle has your collarbone and your shoulder blade, and it attaches onto your arm there. So that's your pectoral girdle, and your pelvic girdle is your hip, basically, where your hip meets your leg. All right, so probably don't need to draw this, but your femur will go here. Okay. All right. So the appendicular skeleton has limbs as well. So here's the basic rundown of limbs. To be honest with you guys, I didn't bother writing notes for this. I mean, everything you need to know is in this diagram here. So your limbs have a basic layout. They have 1 big bone, then 2 slightly smaller bones. All right. Then you have 7 or 8 kind of what are called carpals and tarsals. All right. Then you've got 5 guys that connect these to what are called your digits then, these guys here. All right, so 1, 2, 3, 4, 5. They kind of follow a nice little pattern there. So in the arm, you start off with the humerus. Then you have your radius and your ulna. Then you have your carpals, that's your wrist. Metacarpals is the base of your hand. So basically, carpals would be in your wrist here, metacarpals here, and then you have your digits, okay? And in this case, your fingers. In your leg, you've got the femur, that's the largest bone in the body, your tibia and your fibula. All right, so your shin bone is the tibia, and you've got a small fibula behind that. When you're talking about the foot, instead of carpals, we refer to them as tarsals, that's your ankle, Metatarsals is where your ankle meets your foot, and then digits, they're your toes. All right, so there they are there. Okay, it's just a matter of learning them off, guys. All right, cartilage. So what is it? Cartilage contains collagen, which is firm but flexible. All right. It does not have blood vessels and so is slow to heal. So as a funny coincidence, cartilage is something I'm actually getting repaired tomorrow on my knee because it doesn't have blood vessels. It takes so long to heal. This happened to me 9 years ago and I still have to get it repaired. All right. Cartilage covers the ends of bones. All right. And cartilage protects the bones. It allows for friction-free movement. All right, as well as acting as a shock absorber as well. So long bones then, here's an example of a long bone. So the external structure, long bones like the femur are surrounded by a membrane called the periosteum. All right, so that white, the kind of typical white thing that you see, that's your periosteum there. All right, and the head is called the epiphysis. All right, so if I was to draw this section here is an epiphysis, as is this section here. All right. Both of these guys are epiphyses. Alright. Probably epiphysi. And the long shaft between this guy is called your diaphysis. Alright. Your diaphysis. Okay. And there's the bone rotating there. Alright. Just to give you an idea of what it looks like. And long bones are important because they're the ones that actually make your red blood cells. So your humerus in your arm or your femur in your leg. Alright. So bone anatomy then, let's have a look inside. So that was the external structure of the bone. Let's have a look inside. So compact bone is made of bone-forming cells, all right? 70% inorganic salts such as calcium, so that's why we need calcium in our diet, and 30% protein. This gives bone strength, but a little bit of flexibility as well. You wouldn't want your bones to be super rigid because then they would break very easily. They need to be able to take a little bit of damage. All right. Compact bone is mostly located in the diaphysis, but coats the epiphysis also. So you have a small bit down here, but it's basically this compact bone. It's kind of hard to label here. So it's this kind of region. There we go. It's this kind of region here. All right. Very dense, very compact, very strong. All right. Then you have spongy bone. So that's this guy here. Now, you might be thinking to yourself, spongy? Why the hell would my bone have anything spongy in it at all? And it's actually because of these trabeculae, but don't worry about them. You don't need to worry about that. But basically, it just allows room for red blood cells and white blood cells that are made by the bone marrow. It gives them room to get out, basically. You know, otherwise, any red blood cells that we made or white blood cells would stay stuck inside our bones the whole time. So the spongy bone allows them to escape into blood vessels and travel around the body. All right. So the medullary cavity contains bone marrow. So the cavity, guys, just refers to the tube. All right. So, like, if you can imagine, you've got a tube running through here. Okay. That's your medullary cavity. I've stopped it here. It should really go all the way down to the end there, like that. Medullary cavity, and inside it contains red active marrow. So young people would have lots of this, but in my case I wouldn't have a lot because, well, I've made all the stuff I need to make, really. Yellow marrow is what adults would tend to have. We'd have a lot more yellow marrow than we do red, while young people have a lot more red than we do yellow. And in adults, yellow marrow, which converts to red marrow when needed in the spongy bone. So if, let's say, for example, I have an injury and I'm bleeding a fair bit, then my yellow marrow, which is kind of acting like a storage, will turn into red marrow to help replace any blood loss that I experience. This next slide is higher level. For the ordinary level lads, you can take a breather for a minute or two here. But there is a few slides after this that you will need to be aware of as well. So don't be running off. Okay. So osteoblast is the name of a cell that forms bone. All right, and they work in a very unusual way. So these cells make collagen. All right, and collagen, we know, is kind of like a firm, flexible fiber. And then hard compounds like calcium phosphate form around these collagen fibers, trapping the cell. So what you kind of end up getting is, right, you have your osteoblast, all right, and it makes some collagen, all right, and then that collagen gets surrounded by hard compounds like calcium phosphate, all right, kind of surrounds it like this and hardens it. All right, it traps the cell. The whole cell ends up getting trapped. All right, like this. Okay, and the growth plate is where a lot of this will be happening. So in the bone, right? In the bone, the growth plates are located here and here. All right, that's your growth plates there. And when you guys hit puberty, when anyone hits puberty, they kind of kick off. They start releasing lots of materials that causes the bone to actually grow, and your diaphysis increases in length as well. So here, cartilage is continually made and turned into bone. This process is called ossification. So basically, the growth plate is where all of this is happening a lot and very quickly. So lots of osteoblasts forming, lots of collagen being made, lots of calcium phosphate hardening it up. This is called ossification, which results in your bone being made. All right. This continues until the person becomes an adult. So in your early 20s, maybe late teens, this process pretty much stops. And throughout life, osteoblasts will make bone and osteoclasts digest bone. So this is the thing. When you're growing, your osteoblasts are outpacing your osteoclasts. So as a result, you grow. But eventually, your osteoclasts are operating at the same rate as your osteoblasts. And that's why we average out in height after a while. And then when we get older, these osteoclasts eventually start to outcompete our osteoblasts, which is why you might see in some cases people actually shrinking as they get older. Now, only a very small amount of shrinkage is actually to do with this, but it's actually more your ligaments get constrained and kind of gives older people that kind of hunched over look. All right. And when osteoclasts digest bone, the calcium enters the bloodstream, and this activity stimulates bone renewal. All right. So basically, our bodies are very much aware of what osteoclasts do, and when they digest some bone, the increase in calcium in the blood is detected, and our brain says, "Hey, osteoclasts get to work," or osteoblasts get to work there and make more bone. So bone development is regulated by hormones. Growth and sex hormones increase bone size, and the parathormone helps remove calcium from the bone. All right. When we look at the endocrine system in the future, we will see that in a little bit more detail. Okay, ordinary level guys, chiming back in now. All right, so we're going to have a look at joints. I'm not going to labor over this too much, guys, because joints is something you would have covered fairly well in junior level. All right, so a joint is where two or more bones meet. All right, some joints are immovable. That means they don't move. And you have, these joints are also referred to as fixed or fused joints. All right, and where a fuse is, where joints fuse, you have what's called a suture. So let's have a look. These joints can be found in the skull. Here's a diagram of the skull, and you can see these a lot clearer now, right? So there's a suture there from this skull plate fusing with this skull plate, all right? So they were actually, when you were a baby, these would have been separated, which is why the head has to be so well protected for babies, because they have these gaps between their skulls that just need a little bit of time to fuse together. And the result is these sutures that you see here. Slightly movable joints. So these joints allow for a small bit of movement. All right. The joints between the vertebrae and the spine are slightly movable. Okay. So see the way your spine has a natural curve to it. All right. And it can actually move a small amount. All right. This is because of the ligaments between all the vertebrae, and also you have your collagen discs in between there, or cartilage discs. Ligaments hold the bones in place, and the discs between the vertebrae allow some movement. All right, it's why I can bend over a little bit, but I can't double over because, well, that would break my spine. You need to do lots of training to become that flexible. All right. Freely movable joints are also referred to as synovial joints, and they have a few characteristics you need to be aware of. The first, these bones, the bones in these joints have cartilage covering on the ends with a cavity between each end. I'll kind of go into that a little bit more detail when we have a diagram of one. All right. The bones are held in place by ligaments to prevent overextension. So your ligaments help overextend. Anyone who's had a ligament injury will probably have gotten it from a sport where they overextended their leg, say, and they damaged their ligament that way. The synovial joints are enclosed by a synovial membrane. This secretes synovial fluid, and its role is to reduce friction. All right, because freely movable joints are the joints in your body that move the most, therefore liable to a lot of friction, and therefore need this lubrication to help them not damage each other. All right. So let's have a look. Hinge joint here. So we're going to use the knee as our example. All right. So just if we go back for a quick second. Oh yeah, this doesn't let me go back because we're recording. But anyway, if we at the start we mentioned about cartilage at the end. So I'm just going to draw it in. So cartilage would be found in this area here. It would also be found up the top here, and even down at the bottom of these bones, these guys down here as well. All right, and all along in here. Okay, and there was mention of a gap as well. You can see a little gap there. This makes it a synovial joint because there's a gap there, and inside that gap would be filled with synovial fluid, which is usually a clear kind of liquidy color. Is liquidy a color? I'm not sure, but anyway, it's clear enough, and it allows this free movement to occur. Hinge joints only allow movement in one direction. So when you kick your leg forward, if you push your leg forward, you can only move in one direction. All right. Then this is one of the reasons why they can support a heavy load. So for example, if I was holding, sorry, nearly went over on myself there. If I was holding a weight in my hand and I extended it out like this, all right, I was holding that weight, I would feel it quite quickly. But if I hold it in like this, I can hold it for a lot longer because, sorry, I'm just stand up a bit, hold it like this, because if I hold it like that for a lot longer, or when I hold it like this, I can hold it for a lot longer because hinge joints can actually take on heavy loads. All right. And knees and elbows are examples of hinge joints. So your elbow is an example as well. All right. Okay. Then you have the other type of synovial joint is your ball and socket. All right. And your ball and socket joint allows movements in all directions. All right, so take your shoulder, for example. I can spin it around like this, but I can also go forward, back, left, right, up, down. If people are walking by the window, they're going to think I'm insane. But anyway, that's how ball and socket joints work. But they can't carry heavy loads as a result of that. Shoulders and hips are examples of ball and socket joints, and this will really help look at. So this is an X-ray of a shoulder joint. So there's the ball part, yeah, and it kind of fits into this socket part. All right, and the synovial fluid would be in there. Cartilage would be lining the edges of this bone here and even in here as well, while synovial fluid would be filling that gap. Okay. So a couple of quick definitions that I forgot to mention earlier on. Ligaments are strong fibers and slightly elastic tissues that connect bone to bone. Tendons are strong, flexible, inelastic fibers that connect muscle to bone. So if we look at this diagram that I lifted from the book, you can see this tendon here, and I'm just going to get this. So if you have a look, this tendon here is connecting this muscle to the patella. See that? Okay. And then here are your ligaments. All right. So you've got your posterior and your anterior cruciate ligaments. All right. Very common area for injuries in sport because of all the twisting and turning can cause the anterior one to go very easily. Apparently, the posterior is very rare to go. Apparently. Beats me. But anyway, the anterior one tends to go along. So there's two ligaments there, another ligament here. Oh, hang on, I'm not sure if you can see that. Another ligament here, two ligaments here. All right. You can see the cartilage lined along the bones here and the synovial fluid inside, surrounded by a synovial membrane there. Okay. Handy diagram to visualize what's going on in your joints. You need to know a musculoskeletal disorder. The easiest one is probably arthritis. And if you were, don't know why, but if you were to Google arthritis and find images, you would find that most of the images you get would be of older hands, because basically arthritis is a consequence of getting old. You use your joints all the time, every day, hundreds of times a day. They're going to break down over time. And this is one of the things that can happen. You can get arthritis. Cause is just basically when a joint becomes inflamed. So look at the knuckle joints here. All right, they're clearly very swollen up, very uncomfortable, and can be quite painful. All right, And osteoarthritis is the common type. Basically, it occurs when cartilage wears away over time. All right, any one of us is susceptible to get osteoarthritis. But rheumatoid arthritis is a little bit different. That's when your immune system attacks the synovial membrane, and as a result leaks synovial fluid out and increases friction and things like that, and it's very sore and very painful. But it's actually not because of wear and tear. It's because your body decided that all of a sudden it hates the synovial membrane and decides to attack it. Prevention of arthritis. You can avoid straining your joints, proper footwear, proper exercises. Like if you're into muscle building and things like that, make sure you're using the weights properly. Stuff like that. Proper footwear. A lot of people often complain of pain in their foot after running, and it turns out that they're not running. Like a friend of mine, this is actually not a joke, a friend of mine told us he was going for a run, and he said, it's awful sore running in cons. And we all start laughing, thinking he was joking, but he wasn't. He was actually doing 2 to 3 kilometers of a run in cons, which are very, very flat and thin soled. So it's no wonder he was getting pain in his legs, you know. Treatment. The thing is, there's not really much treatment for arthritis. You can change your diet, you can change your habits and your exercise. That can help. If you have rheumatoid arthritis, anti-inflammatory medication and steroids can help. But ultimately, there's no cure. All right. So near the end now, guys, muscle types. All right. So we had a brief mention of these at the start. So skeletal muscle is kind of the classic muscle that you see. All right. If you typed into Google muscles, these are the muscles you would see. All right. You see that characteristic stripe that they have, and you can move your skeletal muscle voluntarily. All right. So my hand contains skeletal muscles, and I can move it. All right. They contract quickly but tire easily. A very easy test here is take your hand and contract it back and forth really fast and see if you can do it for a long period of time. The odds are you probably wouldn't be able to do it for much more than 2 or 3 minutes. All right. So they do contract quickly, but they tire easily. All right. While your smooth muscle is kind of the opposite. It's not striped. It's involuntary. It contracts slowly and tires slowly. You find them in internal structures. All right, such as your bladder or your small intestine, and they basically do things a little bit more slowly and don't have a lot of mitochondria as a result. But your heart contains a special type of muscle called cardiac muscle, and it contains a hell of a lot of mitochondria because it contracts quite strongly, and it does not tire very easily. All right, which is a good thing. Obviously, you don't want your heart to tire. And it is also involuntary. Another useful thing. You wouldn't want to have control over your heart the same way you have control over your breathing. Imagine like every 5 minutes someone saying to you, isn't that mad? You have to think about beating your heart beating, and you're like, oh my god, that's all I can think about now. Be a mad world to live in. Last slide, antagonistic pairs. All right, so an antagonistic pair is very simple. These are pairs of muscles that have the opposite effects on each other. The biceps and triceps are an example of an antagonistic pair. When one contracts, the other relaxes. And when describing the mechanism of an antagonistic pair, the muscle that causes a joint to close is the flexor, and the muscle that causes the joint to open is the extensor. So, if I was to use my arm as an example here, okay? So when I pull my wrist towards, my bicep contracts, okay? And the joint is closing. So the bicep is the flexor, all right? And the tricep is the extensor. But when I go the other way, my tricep is contracting, the joint is opening up. So this time it's the flexor, and this time it's the bicep that's the extensor, okay? Is that all right with everyone? I don't know why I said that, because this is recording. That is the habit that you get into as a teacher. You say these things even when there's no one in front of you. All right, guys. Hope that was helpful. Just make sure you go over this in your own time, guys, because I doubt, with the way things are going, I doubt we're going to have much time to cover this extensively again. All right. So if you have any questions, just make sure you let me know over Teams or something like that. Okay. All right.